each of the presenters, and then we'll have time for some questions towards the end. So I'd like to welcome our first presenter up on stage. It's Mikael from ICL Fertilizers.
So good afternoon, everybody. Well, for me, the big job to do the first presentation after lunch. So I try to get everybody, well, fixed to it. I'm going to talk about our phosphate recycle project. In the morning, we were talking a lot about sewage sludge ash. But if we have the ash, we also need to make a fertilizer out of it. So this is I'm going to tell the project we are running for a few years already. But first, a little bit background about ICL, what we are. We are a leading global company in specialty minerals, basically focused on food, agriculture, and industrial markets. All the raw materials, all the products we are making, we own by ourselves in different mines all around the world. Well, this one I skip, it's about me. So where we are all around the globe. We are originally from Israel, Israeli state-owned company. Right now we are a commercial one. We have 50 production sites all around the world. 12,000 people are working for ICL, and in total we have 12 R&D centers, also all around the globe. If we are looking in more detail to the plant nutrition, this is the group where the site where I'm working for in Amsterdam. Well, we are producing the products for the innovative agriculture solution. It's mainly here SSP, TSP, Fertilizer Plus, an organic polysulfate mineral. We are winning in the UK, and we are making also fertilizer out of that. Also in the group controlled release, water soluble. And last but not least, where we are going to talk about today, is the phosphates based on 100% recycled phosphate. This morning, I was also asked by one of the persons, when we were talking about, well, recycled phosphate, he asked me, what are the goals for ICL regarding recycled phosphate? And I told him, we have the goal to replace 100% of our phosphate by recycled. Also what we hear this morning, it's not something we wish to do. Of course we wish and we want to do, but it's also a must, because if we are continuing like this, in the end of the day, we are ending up our phosphate reserves, and we as mankind have a huge problem. So the plant where we are all doing this is based in the harbor of Amsterdam. We are established in 1907, and we became part of ICL in 1982. And right now we are producing around 450,000 ton granular fertilizer, everything based on P. And if you're looking here and later on, and this is the part we are going to talk about, this is the last recently added installation, and this is where we store our rock, the sewage sludge ash, and from here we are going to process it in our production plant. The construction of it, we started in 2019. R&D work, however, was already starting years before. I think it was around 2012, 2013, when we received the first samples of sewage sludge ash, just with the question, are we able to use it? At that time, it really looked like, well, it's something far, far, far away. But I can tell right now, 2022, we are there where we want to be. When we were still doing all kind of research and development, we already made a decision to construct an installation that could consume the sewage sludge ash. The only thing at that time we knew is that it could not go through our traditional process. We only knew it was very fine material, so we had to build 3 silos, and from there we had to feed it to our production. And that was the only thing. And from there we started to work. Construction finished in 2019, finished and became operational 2020. Actually, and from there the whole story started, because on R&D everything was running well, and then we had to go in real life, and the next problem came up. We constructed 3 silos where we can store meat and bone meal ashes, sewage sludge ash, and other material. And all the phosphate sources are transported by truck. So we receive them from the local market. We have 2 suppliers, one in the south of Holland and one in the north of Holland, and they are supplying us all the sewage sludge. So a little bit more in detail. The site we are having is based on single superphosphates or superphosphates. So what we are doing in the traditional process, we are receiving rock. In our case, we receive our rock from Israel. From there, we're going to grinding process, and we are going to make the P water soluble. And from there, if we have here the water soluble P, we are going to make the final granule. So what we now did, as shown in the previous slide, we installed 3 silos, and from there we directly go into our production process. So there is no any further processing of the sewage sludge ash. So as it's coming from the manufacturer, we are processing it in our production. So as mentioned before, what we want to do, our goal, is to completely outsource the phosphate rock with recycled phosphate, which can be sewage sludge ash or can be meat and bone meal ash. So where we are today, we're the first, well, first of all, we had to get the unit running. I have to say it took us more time than we hoped, but after around 1 year, we got the equipment running and also the material coming out also running well. We had a first successful production where we replaced phosphate rock for SSP and TSP production. We had a first granulation of P where all the rock was replaced by sewage sludge ash. For last but not least, the product we are producing is the same quality, or having the same quality as the product based on the phosphate rock. And here, the Pura loop is now together with our sales and marketing department is going to be the product we are bringing into the market and developing it together with the help of our sales department. So what we want to do, because we just started our journey, we are now still here in this area, making product with 100% recycled phosphates. From there, we want to start introducing the K, the potassium. Our goal there is to replace the potassium by polyhalite. This is a green potassium source coming from our mine in the UK. And this is the goal we want to have in the end of the year, to bring this kind of product on the market. But still a long journey to go. Continue developing it, and last but not least, we are the leader. We want to be the leader in phosphate technologies. This is our first big project. The coming years, more and more product will come out in recycling the nutrients. So this is my presentation.
Thank you very much, Mikael. I know you need to leave soon, so if anyone's got a question, perhaps they'd like to ask now. Gentleman over there, you might have to shout.
It's a very good question. I think this question was also raised in the morning. Yeah, well, the question was how to bring the product on the market and into which market. And I thought it's a very, very good question. Because the product, well, it's a different product. It's a green product, so we're also focusing on the bio, not bio industry, but the, how you call it, the organic. Thank you. Organic farming. It's one of our target markets where we want to promote the product to. Yeah, we are mainly talking about Europe. Yeah. Correct, correct. Yeah, there are still a lot of, basically in legislation, a lot of things going on there. We are not there where we want to be. We have now a temporary permit to bring these kind of products on the market, but not in the, I'm not 100% sure regarding organic farming. But for in the way, also was I'll talk about this more. We are now getting ready that we have the product. Now, unfortunately, we have to wait for a big part on legislation.
Two more questions. So, gentleman here.
Can you have an idea about the cost of these products in comparison with the plastic?
Regarding production cost, there is no difference. No. What we did is just installing the new equipment. From there, it directly goes into our isolation line. And from there, the production process is similar to our current production process. Including, depending on the time if you are looking today, I think we all know what the phosphate market is doing. Russia is one of the biggest suppliers. Well, they are not supplying a lot of rock at the moment. Prices of the phosphate are going triple or even higher. So right now it's a good product with well, we can produce it for a good price. Let's say it like that. At the end of the day, the salespeople of course have to sell it. It's a different. It's for them. I can produce it in a good price.
I'll do one more question over here. You look quite keen.
Sorry? In the beginning, we were targeting only replacing a few percentage. So few percentage in the rock replacing by sewage sludge. From there, we saw it was not running that well. So the products I was showing here in the presentation, there we replaced 100% of rock by sewage sludge ash.
Okay, final question.
Regarding bone meal, are you able to buy it in competition? In Austria, it is the cement industry which has the full hand on it. How is the legislation, the legal base in your country?
First regarding price, I think it's the same, well, more or less same answer for regarding the sewage sludge ash. Right now, it's a good. We can buy it for a good price in the market. I have to say, legislation from meat and bone meal ash perspective, if I'm talking about the product we put on the market, it's easier because meat and bone meal ash, it's, I would say, almost one-to-one comparable with a run of pile with the product we have today on the market. So legislation from there, it's much easier. And I think in the end of the day, it will also, because of that, it will be easier to put those kind of products on the market.
Thank you very much.
Thank you.
Okay. Yeah. Okay. So for our next presentation, we have Marc Sonvieux, nearly, from Prayon in Belgium.
Okay. Good afternoon, everybody. So I will speak in this presentation about the recent development that we have made in Prayon to improve technology for phosphorus recycling, and mainly recycling of phosphorus from sewage sludge ash. So this is to start a little bit the network of the activities of Preon. So the base of the business of Preon is the production. So we have production activities with 4 sites where we employ about 1,200 people. And we produce phosphate for more than 130 years. So we know phosphate. And the capacity is more or less 300 tons per day of phosphorus. So the sites are in Belgium, 2 sites in Belgium, and 1 site in France, 1 site in US. And mainly in Belgium, we are producing phosphoric acids and phosphate salts addressed to the technical market or the food market. The second important thing is related to the market. So we know very well the phosphate market and the different fields of activities. So you know the different qualities of phosphate that can be produced, starting from the electronic grade, small volume, high price, pharma, food market, which is very well protected by legislation for quality and source of raw materials. And then there is the branch, which is the technical market. The technical market is the market that addresses, for example, the steel industry, horticulture, or a specific application for cleaning and others. And this is a good market for recycling phosphate because of the volume of the market and of the added value of the product. So we focus on that topic for our activities in phosphate recovery. And then we have animal feed and fertilizer, bigger volume, lower prices. Animal feed, there are restrictions also at the legislation point of view for application of recycling phosphorus in that field. But with Preon, we are active as producer in food technical and as technology supplier in animal feed and fertilizer technologies mainly. The next point is the innovation. So innovation is key for sustainable business. So we have 3 R&D centers, located 2 located in Belgium, in Angis and Puurs, and 1 located in Bulgaria that has been acquired from Ecofos a couple of years ago. It's called Technofos. And with those 3 R&D centers, we can address the different steps of a project development and a process development, starting from the pre-feasibility laboratory studies, going to the validation of the concept at higher scale, to the pilot operation, and also semi-industrial activities. And so during this field of development, of course, we estimate and evaluate CapEx and OpEx of the different technologies, and we can do the engineering and the conception of the different plants. So that's what we are doing for all our clients. And for all the technologies we are developing in Preon. Then Preon is a technology supplier. So we have built more than 130 phosphate plants, mainly phosphoric acid plant. So we know how to conceive and build plants in 30 different countries with 65 different kinds of phosphate rock. And I should add to that with several kinds of sewage sludge ash, also mainly in Europe. And what is very important also is that we have a portfolio of technologies. So the portfolio of technologies goes from the phosphoric acid production to the purification of phosphoric acid, of gas treatment, evaporation technologies, and several others that can be combined together to bring an answer to the challenges of the raw material we are using. So we use low-grade phosphate rocks, we use secondary phosphates, we use spent acids from the industry also, even in our plant in Angis. And so we can really combine our know-how to get the right answer to the right problem. Then in 2020, Preyon acquired Ecofos technology that was known for the phosphate production, phosphoric acid production from fly ash, that we continue to develop and improve, and we can call it now a Preyon Ecofos loop process. And it's what I will more detail in this presentation. So the concept is relatively simple. So we take the fly ash, we dissolve the fly ash in phosphoric acid. So phosphoric acid is coming from recycling out of the process, and a small makeup if necessary. It's not always necessary, it depends a little bit on the composition of the fly ash. After digestion, so we dissolve the phosphates, we don't dissolve the impurities. So the impurities are removed as a residue cake after filtration. Then we have 3 stages of ion exchange, and that's the key of the process, is to have a specific separation between calcium, magnesium, iron, and aluminium. So with this process, we have the phosphate that is purified, we have the removal of calcium, magnesium as chloride, iron chloride, or aluminium chloride. Iron chloride, aluminium chloride can be used in the wastewater treatment plant. Then, after the evaporation, we can recycle the phosphoric acid for the dissolution of the ash, and we can obtain directly the technical grade phosphoric acid. So from this, we go to this quality of acid. So for us, it's important, as I explained already, to go to technical grade phosphoric acid because of the volume, because of the price, because of the legislation that allows to use secondary phosphates, and also because we know this market. And Preyon can participate in the different projects as off-taker for the phosphoric acid. So we don't only supply technology, but we supply also the market. So we can help to put the product on the market and distribute the product. And the product that is done with this technology respects the specifications we have for technical grade acid. So this is some pictures of the validation that we performed in our demo plant in Bulgaria. So we have the phosphate ash, the fly ash, is brought by belt conveyor to the reactor, where we have a simple reactor where we have the addition of phosphoric acid, recycled phosphoric acid. From this, we have the filtration using press filters. We remove this residue, and we obtain a phosphoric acid, untreated phosphoric acid, that contains calcium, aluminium, and iron as the main contaminants. Then we have the treatment with the ion exchange. So we have the 2 similar ion exchange systems for calcium, magnesium, and iron, and you have a specific one for aluminium. And during the process validation, we recover the different fractions of the purifications to identify the best fraction of the side products also for the use in a wastewater treatment plant. Then we have the evaporator, and this is what you don't see because it's so clean that you don't see the phosphoric acid that is produced with this process, even at high concentration. So we go to 54% to 62% P2O5 as product. Important information. So we've performed this with 3 different types of ash, very different in terms of content of aluminium, iron, calcium, but also sulfates. We performed the test during more than 12 weeks, and what we observe is that the process is stable and robust. So this means that we can absorb the variation of the ash and have a flexible process that can use different quality of ash. Very important also is the global yield. So the global recovery of phosphorus is between 96 and 98%. So this means that this is quite a good performance because we recover most of the phosphorus into the phosphoric acid. And then the quality obtained is presented on the table. So you see that for the main elements, we pass from the percent to the ppm. Calcium is almost completely removed, same as magnesium, aluminum and iron. Also, what is important for technical application is the monovalent ions that are also removed, sodium, potassium. Arsenic needs a special treatment to be removed, but that's a technology that we have in our portfolio, so it was not applied in this case. And then for the heavy metals, you can see that we remove most of the heavy metals, even below detection limits for cadmium, lead, and barium. What is important also is the removal of the silica. So silica is not dissolved by the process, and that's important because if you dissolve silica, you might have to some issue of scaling in your evaporator, for example. And there is no sulfate addition, so this typical example contains quite a lot of sulfate, and so the sulfate, 77% of the sulfate there is removed. If there is no sulfate in the ash, of course, there will not be any sulfate in the final product. So as a conclusion, so we compared to the previous presentations we did on this technology, so we optimized the digestion conditions. So we optimized the yield, so we obtained very high recovery. And we minimized the phosphoric acid makeup. So even in some projects, we could avoid completely any makeup of phosphoric acid. The second big task we had was to optimize the ion exchange. So we reduced drastically the HCl consumption and the water consumption. By doing that, we also managed to reduce the volume of the resin to be used and the cost of the resin. Very important for us is also to split the different species between aluminum and iron as co-products, and finally we improve the quality of the product. So what we see as a big advantage of the process is that it's very flexible for different ash. It can even be applied to certain kind of phosphate rock. So it's in our standard field of activities, let's say. We don't use any sulfate or sulfuric acid in the process. Sulfate gives gypsum. Gypsum gives nightmare and precipitation scaling. So we avoid the sulfate. There is no solvent or no special chemicals. It's based on dissolution phosphoric acid, ion exchange, regeneration with HCl. So that are the steps that are quite simple and common, so it's easy to scale up. From a pilot to industrial scale, it's a question of volume of resin, simply. And another advantage is that we can use HCl in Europe. HCl is available as a byproduct of the polymer industry or the caustic soda industry, or even some fertilizer like potassium, SOP production, sulfate of potassium production that produce also HCl. So it's also leverage to be able not only to use the waste phosphate sources, the secondary phosphate sources, but also the secondary or the waste HCl sources. So that's also important for this application. We validated the process at pilot scale with different ash. What is important to keep in mind, and that is true for all the technologies, is what goes in must go out. So if you have an ash with impurities, you need to get rid of the impurities. So there are two streams that needs to be considered in the different project that we are making. Is the residue outlet, so the insoluble part of the ash, and this residue outlet is stabilized because it has been leached with phosphoric acid, so it's not a dangerous waste. But the outlet of the local specific project needs to be defined, as well as the solution of calcium magnesium chloride. It's a very good de-icer, but that needs to be concentrated to be valorized, or is very clean and can be disposed of in the sea, for example. Then, as Prayon, we are bringing to our customer in that field of activities a business solution, because we come with the technologies, of course, the know-how of industrialization, of industrial process, our commercial experience in phosphate. Also, we make the full validation of the process at the different scales with the raw materials of our customers to give the guarantee of performance of the process. So performance in terms of capacity and quality mainly, and specific consumptions, of course. And then we can come with a package where we can offtake also the phosphoric acid. That's it for me. So enriching daily life through phosphorus chemistry. That's our mission.
Thank you very much, Mark. We'll have questions at the end of the remaining presentations, so please take a seat. So our next presenters, I'm going to try and pronounce the names correctly, is Leon Corving from Wetsis in the Netherlands and Bengt Hansen from Kemira in Sweden.
So, my name is Bengt Hansen, ladies and gentlemen, and we have Leon Corvin here to the right of you, left of me. So we have a joint presentation about Vivimark and tell a story about how to develop a new technology for phosphorus recycling. We start with the why, when it all began, this story. It was because there were already 10 years ago technologies looking into extracting from sewage sludge ash, and then we had the struvite track as well. Both these tracks have advantages and disadvantages. If you look into the incineration plants, they are quite expensive to invest in, and the struvites, the recovery, they need a BioP process, and also the yield of phosphorus recovery is fairly low with the struvite. In reality, a lot of the wastewater treatment plants use coagulants for phosphorus removal. The coagulants precipitate phosphate, but they can also remove particles from the wastewater and then also improve the carbon footprint and improve the energy efficiency of the wastewater treatment plants. Coagulants are based on aluminum iron salts, where iron is the dominant one used in the wastewater treatment. You can see here on the presentation how much of enhanced biological phosphorus removal that is used in some countries, and combined chemical and enhanced biological phosphorus removal, and for instance UK and Sweden, where we have mainly chemical precipitation and biological treatment. So a lot of the wastewater treatment plants still use coagulants and iron, and they will continue to do that for a long while. Iron is also present everywhere in a wastewater treatment plant. It comes already from the beginning into the water, from the pipes, from the groundwater, and in some cases also iron is dosed to suppress sulfide formation in the sewage pipes. Then coagulants can be added in the primary, secondary or tertiary treatment, as well as into the digester. So iron can be used in very many different positions in the wastewater treatment plant. And here we came to the question on how to use the iron phosphate and work more with that. And with that, I'll leave over to Leon.
Yes, actually that understanding that iron is sort of inevitable in a sewage treatment plant was the start of a research collaboration. So already 10 years ago at Wetsis, we identified that, well, actually nobody is looking at the iron-phosphorus interactions, and why not? And should we? And it was always regarded as something iron is bad, you cannot recover phosphorus when there's iron. So we thought, let's start looking into these interactions and see if we cannot make use of the iron and instead recover it. So we decided to set up a research collaboration, and actually Kemira was one of the, and STOA, the Dutch research organization, and Kemira were the first ones to join our research collaboration. And well, as you can see, Camira had also various other reasons than just the content of the research and our research proposal to start off with. But this started us off to on a journey on trying to see if we could make use of the iron in sewage treatment plants. And we did that in not only with Camira, but also with quite some other partners. So our main research partner was Delft University, the group of Professor Mark van Loosdrecht, and with researchers at WETSUS, Camira, and we had already various end users, sewage treatment plant owners, already from the beginning involved, like Water Authority Brabantse Delta from the Netherlands, Waterschapsbedrijf Limburg also from the Netherlands, and Van Center Zuid from Denmark. And with all these people, we've been working on this Vivimag development. The basis of the Vivimag development was when we started off, we first started with fundamental science to first understand how is iron actually bound to phosphate in sewage treatment plants. A lot of people think that iron 3 binds with the phosphate to get something like strangite, iron 3 phosphate, but that actually cannot form in a sewage treatment plant. And what we've seen that, well, in the main treatment line, you can find various forms of iron phosphate. But when you start looking at the sludge digester, you will only find one main phosphate mineral, and that's vivinite, ferrous phosphate. And actually on the graph that you can see here, you see that depending on the molar to iron to P ratio in your digested sludge, the percentage of total phosphate bound in vivinite sort of linearly goes up until you reach a percentage of roughly 80 to 90%, and then it levels off because, well, 10-15% of your phosphate cannot be present available for the iron because it's in the bacteria's DNA or other stuff that makes up the bacteria. But interestingly, we saw that if you dose enough iron, up to 80% of all your phosphate can be present as ferrous phosphate, and that's quite a huge amount, and that would represents a high recovery potential. The only thing is that these particles, you can see them on the picture there, are very small. They are only 50 to 200 micrometers small. So that actually presents a separation challenge, because how are you ever going to get out these small particles from something like sewage sludge? But we looked at it with a microscope, and we saw that we confirmed that these particles are free, so they are not affixed to the sludge matrix, and they are paramagnetic, as you can see on the small GIF on the slide. So and paramagnetic means that they are not magnetic by themselves, but if you put a strong magnet next to it, they become magnetized and you can get them out. And here you see our first proof of principle that we published in 2019, where we were able to remove these vivinite particles with a magnetic separation equipment. And actually this is a model, a microjoule separator, that when it works at this scale, the professor at Delft said, well, if it works there, it will also work at full scale. Well, we believed him, and therefore we went to the next scale. And this is how it would look when you scale it up. This is a commercial-sized wet magnetic separator that you can buy from a company like Autotech, and that's been used in the mining industry to upgrade iron ores. And it works like, it has a ring that turns, there's a bath of sludge, it dips into the sludge, and then when the ring is in the sludge, there's a big magnet that magnetizes all these cassettes, which are consisted of a lot of small rods. So the vivinite attaches to the rod, turns out of the sludge and out of the magnetic field, and can then be flushed off quite easily and recovered. So we demonstrated this in 2019 at pilot scale at the sewage treatment plant in the city of Breda in the south of the Netherlands. And here you can see our pilot separator. This was the smallest size commercial magnetic separator that you can get. And it processes about 1 cubic meter per hour of sludge, which represents a population equivalent of 20,000 people equivalents. And in this pilot plant that was funded by ART Raw Materials, EU fund, we demonstrated that we could get 80% of the vivinite that was present in the sludge, can get it out also with this wet magnetic separator. And we also published this work in Water Research that you can look it up for the details. And what does this then mean? And it means overall that we can recover 60% of all the phosphate that's present in the influent of a sewage treatment plant through this approach. Because if you look at the influent, 100% is phosphate. Approximately 90% of all the phosphate goes to the sewage sludge through iron dosing, for instance. And in the digester, 80 to 90% of this 90% is present as vivinite. So 75% of the influent P can be present as vivinite and recovered. And with our magnetic separator, we can get 80% out. So overall, we can recover 60% of the influent. And that's a much higher recovery percentage than, for instance, with struvite precipitation, where you can typically only get 20 to 30% if you have a good plant. So this is quite a nice prospect, and it can also be quite easily retrofitted into a sewage treatment plant, because the only thing you have to do is that if you have your sludge digester and you're dewatering, that you install your magnetic separator between the digester and the dewatering to get out your vivinite. And the added bonus is that you reduce the inorganic content of your sludge, so you also reduce the sludge volume with roughly 10%. And that pays for the installation of your magnetic separator. And well, that was the work that we did, and now Bengt is going to take over. It's also a bit of a symbolic phase, because as Wetses, we've been working on the whole research development, and actually now we've handed over the patent to Kemira, and now Kemira is the party that's going to further commercialize this whole technology.
Yeah, thank you, Leon. So the next step for us is to continue to verify the technology, and that we will be doing by building a pilot plant, and this one is under construction and will be placed in Viola Schönebeck in Germany very soon, next week or next week after that. So it's a 40-foot container, and the capacity, Leon said up to 20,000. I'm a little bit more modest. I say more than 10,000 people equivalents, and it's a fully automated plant. So why do we do this again? We already have done a pilot test. Of course, we need to verify the technology, and we need to verify it at different kinds of wastewater treatment plants. So in this case, it's a BioP plant we will start with, and then we will work with sludge, raw sludges, non-digested sludges, etc. So we will evaluate this technology on different kinds of wastewater treatment plants. We also need to understand the availability of the equipment. How long will it last? When do we need to clean it, and so on? And we need to generate data for the demonstration plants and create enough vivianite to test different routes of the vivianite, because there are quite a few routes that we are considering. Just a few pictures from our workshop is the container here. And if you go inside the container, you have the magnet, different color this time. It's about 1 meter in diameter, 1 decimeter wide, and can take 10 to 20,000 P equivalents. And here we see a little bit more in detail the magnetic separator of the pilot plant. There are some possibilities to use vivianite, but we have to remember that there are a lot of directives we have to fulfill: end of waste, REACH, fertilizer directive, etc. And we are certainly aware of that vivianite has a too high iron content to be used directly as a phosphate salt according to the CMC of that. But still, vivianite is has a good solubility with lactic acid, so it's fairly available and can be used directly in agriculture. It could also be used as an iron fertilizer, which is something it's already done. For instance, in olive plantations, the citrus plants, vivianite can be used. It can also then be used in biogas plants to suppress hydrogen sulfide, and you will get more phosphate back that way. And of course, there will be and are already developing technologies on how to split the iron and phosphate to get more enriched materials out of it. So iron can be used for water treatment again, and more high concentrated, high quality phosphate can be used for other applications. And then a very long shot, therefore put in the brackets is that there are batteries under development, lithium ferrous phosphate batteries, and they use ferrous phosphate, which is the same as Vivianite. So maybe in the future we also can produce batteries out of the sewage sludge. With that, I think Leon takes the lessons learned.
Yes, so today we not only present a new development, a Vivimag development, but I think it's also nice to see what were the lessons learned in this whole development, because I think the nice thing about this whole technology development is that we started already from the beginning with a clear market vision that we wanted to find a solution for sewage treatment plants that use iron, and that we were able to involve the end users and parties like Chimera already from the beginning. And that was really helpful in the fundamental part of the research to get focus on where we wanted to go. That also helps to create trust with all the different stakeholders to quickly go to practice and do these pilot tests and go to the upscaling phase. And one of the other key learnings, it's a long road, so that's why you need this level of trust between different stakeholders and already start networking between these others already from the beginning. And the second learning is, of course, that it's always the acceptance of new products is always too slow, and maybe that's also partly inevitable because the regulators cannot predict what will be coming on the market, so they always will have to react to what you are doing. But it would be nice if there would be quicker procedures to take up these new products and get them to the market. Thanks for your attention, and we're open for questions.
Thank you very much. So as I said before, we'll take questions after all the presenters have been, so please write down any questions that you have. You can also use the Swapcard app, so especially anyone listening online, please do post questions on the Swapcard app. So our next presenter is Yariv Cohen from Easy Mining.
Thank you very much. My name is Yariv Cohen. I'm the head of research and development at Easy Mining. And we heard in the first beginning of the day that it is important not only to talk, but also to do. And we are a company dedicated to actually do things and to make circular economy in reality. And I would like to share with you a little bit about our work on recovery of phosphorus, nitrogen, and potassium. Short a little bit about Easy Mining. We are a daughter company in the Ragn-Sells group. Ragn-Sells is a large Swedish recycling company that handles about 6 million tons of waste per year, about 2,700 employees, active in 4 countries, in Sweden, Norway, Denmark, and Estonia. Easy Mining, we are about 40 people in 3 locations, 2 in Sweden and 1 office in Berlin, in Germany. We are currently, we belong to a business area in Ragn-Sells that work with the future, with developing new technologies to recover commercial products out of wastes. We focus now on these 4 technologies that we are commercializing. Ash to phos, which I will focus now on, which is about phosphorus recovery from sludge ash. We have ash to salt, which is a technology to treat fly ash from waste incinerators, in which we can recover the salts. We can recover potassium chloride, which is a valuable fertilizer from fly ash from waste incineration. We have a technology for producing monoammonium phosphate in an energy-efficient way that has application in the fertilizer industry. And we have a new technology for nitrogen recovery from wastewater. Here you can see, to the left, you can see the first plant that we are building north of Stockholm for recovery of salt, potassium chloride, sodium chloride, and calcium chloride from fly ash, from waste incineration. It is the biggest investment in circular economy in Sweden. It's a 75 million euro project. In this plant, we'll have a maximum capacity of 150,000 tons of fly ash per year, coming from 15 incinerators and also from nearby waste incineration in a conveyor directly to the plant. In the middle photo, you can see the ash-to-phos plant that we intend to build together with our partner Gelsenwasser in Germany, in Schkapau, with a capacity of 30,000 tons of sewage sludge ash per year. It equals about 3.5 million person equivalents. And we have just now submitted the permit for this plant, and we have also submitted the permit for a plant in Helsingborg in the south of Sweden with the same capacity. To the left here, you can see our technology for recovery of nitrogen. It is an EU Life project. We have new technology that we can remove nitrogen by chemistry, chemical precipitation and not stripping, and we intend to commercialize this technology in end of 23. Here you can see a scheme of our technology for salt recovery from fly ash, from waste incinerations. As you know, fly ash contains a lot of salts, which makes it difficult to dispose. Therefore, we developed the ash-to-salt technology, which is actually that we wash the fly ash with dirty water. We can use this technology as a water purification. We dissolve the salts in the dirty water. We remove the heavy metals. We remove the organics, and then we also recover the ammonia nitrogen, if present, in form of ammonium salt. And we can crystallize and separate the salts differently. We get salts of 99.9 purity. And this is the plant that we are building north of Stockholm. Regarding nitrogen recovery, we have a technology which is based on that we add a chemical to the wastewater, we precipitate the nitrogen, we remove it, and we can regenerate the chemical and at the same time recover the nitrogen fertilizer. And ash-to-phos, which I will focus on, which is the subject of this conference, is a wet process for recovering of phosphorus from sludge ash. The raw materials are hydrochloric acid and lime. The process is a robust process. It is based on chemical precipitation. We separate the heavy metals for disposal, and we recover phosphorus in a clean calcium phosphate form. And we recover also iron and aluminium separately as commercial product, ferric chloride 30% and sodium aluminate 38%. The advantage with the ash-to-phos process is that we recover more than 95% of the ash as commercial product. The iron and aluminium we recover separately in a commercial form. And if you want to scale up the technology, it is not only phosphorus that you need to recover, you need to handle all the metals in the ash. As you know, there is advantages of incineration of sewage sludge. You have detoxification, you increase the phosphorus concentration in the ash, but of course you have all the metals. You have iron, you have aluminium, and you have the heavy metals there. So to use ash directly in the fertilizer industry is problematic. You need to have a dedicated process that actually separates the metals from the phosphorus, and this is what we do with the ash-to-phos process. Here you can see the extent of detoxification in the ash-to-phos process, and it's very important if you process ashes that you actually separate the heavy metals from the phosphorus. And with the ash-to-phos process, we get a separation that for many heavy metals that is about 99%. So actually the recovered phosphorus product is the purest phosphate raw material on the market today. Here you can see the analysis of the product. It has about 17% phosphorus. In P2.5 it's about 38% P2.5. You can see the fluorine content is extremely low, so actually this product is of feed quality. We have done tests with feeding pigs and chickens, and it works really well. Unfortunately, there is a legislation hinder in Europe that you're not allowed to use material originated in wastewater for feed. We believe that in future this will change, and this is an excellent feed raw material. Of course, this material can be used as a fertilizer. It is completely soluble in dilute citric acid, and we have a fertilizer company that are interested to granulate it and use it as a fertilizer. And it can also be used as a raw material for producing any existing phosphate compound in the existing processes. So it's a very flexible material. And as I said, it's not only to treat the phosphorus, you need to handle all the byproduct from the process. And in this process, we recover the iron and aluminium as commercial products. You can see here recovered ferric chloride of commercial concentration and quality that can be reused in wastewater treatment plant. And the residue, the silicate sand, we have actually been doing tests with the cement and concrete industry, and we can see that if it is treated in a certain way, we have porcelainic effects that we can replace 20% of cement in concrete. And in that way, you can actually reduce a lot the CO2 emission of cement production by having this material into the cement and concrete industry. Here, we'll go back. This is a movie, but I cannot start it. This is the illustration of the ash to phos plant that we intend. Let's see if I can start it. No. Maybe you can start it. It's a movie. This is a 3D model of the plant that we applied for the permit with our partners Gelsenwasser in Schkapau in Germany. As I said, this plant has a capacity of 30,000 tons and will produce 15,000 tons of recovered phosphorus, and we see that there is a great interest and demand from the industry for this recovered material. Thank you very much.
Thank you very much. So as before, please store up your questions so you're ready to ask them at the end of the presentations. So our next presenter I'd like to welcome to stage is Henk Arts from N2 Applied.
And now for something completely different. And I always wanted to do that, and this is my opportunity. And that's a Monty Python thing for those who don't know. Because I'm going to talk a little bit less on phosphorus, but more on nitrogen. And as you can see, N2, I guess you all know where that stands for. Good afternoon. Thank you for being here, and thank you for listening in. My name is Henk Arts. I work for N2 Applied. N2 Applied is a Norwegian company, and I'm Dutch. I'm based in the Netherlands, and I'm responsible for the European business development for N2 Applied. So as an introduction, N2 Applied was founded in 2010 by two founders, Grete Sundsteby and Rune Engels. Grete has a background as an entrepreneur, has done several startups already, and Rune Engels has a background from the fertilizer industry. We are based in Norway, we have our test center there, and we have an office in the UK, and we have an office in the Netherlands. We are around 40 people working there now on the agronomy side and the R&D and the business development. And what we have been doing, and actually the most people have been coming in from 2017, right? The first years they have been working on the idea that I'm presenting here. But in the last 4 or 5 years, we have been substantiating what we do in the field, and we are now ready to make this commercial. I guess you're all aware that we have a challenge on how to feed our growing world population without overwhelming our planet. That's true on the phosphorus side, but that's true on the nitrogen side as well. And you might be aware as well that we are actually feeding around 50% of the world population with chemical fertilizers. So we need chemical fertilizers to actually grow the population as well. But chemical fertilizer has quite some negative effects on climate change, nutrient pollution, soil degradation, and biodiversity losses. And that's something we want to tackle. Nitrogen is vital in securing our world's food supply. Like I said, I guess if we wouldn't have nitrogen fertilizer, I guess the world population hadn't increased as much as it has now. But basically we are feeding the crops, we're growing crops with both chemical fertilizer and livestock manure. There's a challenge on the chemical fertilizer production. It's being done in large industry with fossil gas or fossil coal even largely. But there's also a challenge on the livestock manure side. There's quite a lot of losses of ammonia and greenhouse gas emissions on that side as well. And basically that is what we try to tackle. We are trying to shift a linear supply chain of fertilizer in something that's circular. And like I said, chemical fertilizer is being produced in large plants using fossil substances to actually produce it. There's quite a lot of losses from laughing gas, from methane, from ammonia, both in the production but also when you put it on the field. And then also from the manure side if you feed it to livestock. What we try to do is put the technology on the farms, so bring it from centralized to decentral, treat slurry, treat the manure, and make a fertilizer locally to substitute chemical fertilizers. And this is how we do it. So we have developed an N2 unit. It's basically a machine that uses only air and electricity to treat a slurry. And a slurry can be anything liquid, either a livestock slurry or a biogas digestate or potentially something from a sewage plant. We produce something we call NEO, nitrogen enriched organic fertilizer. And I'll explain how this works. It's a two-step approach. The first one is a plasma technology. And basically this works like lightning in the air. When you have lightning in the air, there's so much energy into the air that the triple bond of nitrogen actually breaking. So we actually produce a nitrogen oxides gas. We do this in a small box. Again, this is like a natural process, but we do it in a small box. The second step, we mix this gas into a liquid stream. This can be a slurry, a digestate, as long as it's liquid, we can do it. And there's a number of things happening then. We actually add nitrogen from air directly into the slurry. So there's a lot of technologies about recovery, getting nutrients out. We're actually putting nutrients in. And while we put nutrients in there, we produce them actually as nitrate and nitrites. So basically, at the end, we have an ammonium nitrate solution. One of the effects that we have is actually that it lowers the pH. This is without adding chemicals, so it's part of the process. One of the steps in the process is actually lowering the pH. We know from a fact from fertilizing that when you lower the pH, this stops ammonia emissions from the liquid fertilizer. But this process also stops methane emissions. And that's a two-part. That's one, the pH effect, but the second one is the sanitation or hygienization effect of the plasma technology. Basically, the nitrogen oxides is a reactive gas. An extra benefit is that the manure smell is removed, so it doesn't smell like manure or doesn't smell like a bad smell liquid anymore. This is just an example of how this could look like when you have an untreated slurry. Let's say on average in livestock you would have around 4 to 5 kilograms of total nitrogen. Half of it would be organic N and the other half would be ammonia N. And basically when you put it on the field or when you have it in storage, you lose between 20 and 90% into the air or into the waterways. So 50%, that's the red box here, of the ammonia is actually lost. What we do is we more than double the ammonia N content. That's the darker green part of this. But this also locks in, due to the pH effect, the ammonium. So instead of almost doubling the content of nitrogen, we actually triple or even quadruple, no, that's the wrong word probably in English, but 4 times make the availability of nitrogen better. What we have been doing in the last 4 or 5 years is substantiating, documenting this effect. And you can easily show that the process works, right? You just turn on a machine and you do analysis and you can show that the effect is good. But if you want to show it on the field with trials, then one trial is no trial, right? You have to do it on several crops, several regions, different soils, etc., different weather types, and that's what we have been doing. And we show that we stop ammonia emissions from this fertilizer, from this liquid fertilizer. So in the left, yes, left. In the left side, you see the curve of ammonia emissions from an untreated slurry, and you see that in the first 4 days, there's quite a lot of ammonia emissions. Even in the first hours, there's a lot of ammonia emissions. In our treated product, the plasma product, you don't have any loss. The lower curves are both the nitrogen-enriched organic fertilizer, the plasma-treated, and a general chemical fertilizer. The middle one is showing that we stop methane emissions. This is basically a digestate. If you would take a biogas digestate and you would put it on the field, if you have it in storage, you have a lot of methane emissions. The methane emissions, the methane production doesn't stop when the liquid leaves the biogas plant, right? So here it shows on the right side in this graph that the NEO hardly has any methane emissions anymore. And on the right side, and it might be the most important one, is actually showing a number of trials that we've been doing, showing that on average we have 40% higher yield if you compare untreated with our NEO-treated slurry. And I say on average because it's never the same. As example, in 2018 we did trials, and you might remember in 2018 we had 40 degrees everywhere in Europe, and then trials make no sense. They're going to be inclusive, non-conclusive, nothing grows, right? So there is quite a difference in there, but on average we show the effect is really high. And if you look at the footprint on the farms, the carbon footprint of farms, this is a study, we did a life cycle assessment with Arla in Denmark based on Danish dairy farms. The baseline farm is here on the left. In Denmark you can acidify slurries with sulfuric acid to make, then you don't have to inject the slurry into the soils. This reduces the footprint with 12%. Biogas on the plants, which is the middle one, reduces the footprint with 16%. But our technology, when you would put it on Danish dairy farms, would reduce the footprint of these dairy farms with 27%. And the combination of our technology and biogas is even bigger. This is what it looks like. So compared to the large industry pictures and the centralized production examples that we've seen, we are actually making a small unit, right? This is a 20-feet container. You can easily put it on the farm. It only needs an electricity connection to operate. All these units are connected to internet so that we can remotely control them and support them. And it's easy to integrate. And we can use all existing agriculture equipment to actually spread the slurry. So there's not a big deal to do this on the farms. And this is attractive for the farmers. I don't know if you read the news from the Netherlands on the ammonia emissions our farmers need to reduce now. There's a lot of discussion about it because the farmers are basically obviously not happy about it. But this kind of technologies can help farmers to increase the yield with more nitrogen in the yield, but at the same time meet their environmental goals, reduce their ammonia emissions. They can make full use of resources, but also apply slurry with precision, because normal slurry you couldn't apply with precision to crops. It has to mineralize first, it can take 2 to 3 weeks, you lose a lot of nutrients. But with our NEO, you can actually do this. And on the phosphorus side, we actually improve the NP balance, right? Because if you add more nitrogen, your NP balance goes up. There's a lot of over-fertilization, and this effectiveness of NEO actually helps solve that. And an extra one is that we can utilize variable electricity. We can easily stop the system. So potentially you could start when electricity is cheap and stop when it's getting more expensive. Or you can only run at night or when the wind blows, right? So that's a system that can actually be used as power to X. And basically we have a power to N, right? It's a nitrogen production. We have substantiated that we can increase or improve the footprint with 30%. We can increase the average yield with 40%. We can reduce air pollution with 50%, and it's 100% precision fertilizing ready. We have been proving this in a number of markets, mainly in the Nordics, UK, Netherlands, and also in South Africa, actually. And we worked with independent renewable institutes and research organizations that have their reports that can substantiate what we actually say. And we had 9 full-scale pilot installations in Scandinavia and UK and Netherlands. And this is the pilot installations to solve the first teething problems of our units. And now we are developing our first commercial units to bring to the market. And, well, basically our mission is to fundamentally improve global food production by increasing yield and at the same time reducing emissions. Thank you very much.
Thank you very much, Henk. So our next presentation is by Arttu Lassonen from NDEV. I hope I pronounced that right. After this presentation, we'll have a short video and then we'll have questions before break.
So hello, my name is Arttu Lassonen. I come from the Finnish cleantech company called NDEV, which develops technology for the thermal municipality wastewater sludge treatment. Our background is in Lappeenranta University of Technology in Finland. We have been developing this kind of technology maybe 13 years now, and at this phase our first pilot plant is ready and working more or less well in Rovaniemi. The idea compared, for example, other examples what we heard today beforehand in Zurich Canton, for example, is that we can make almost the same kind of process but more affordable, if not even frugal way, that this is a little bit more simple. For example, it's non-pressurized if we compare to the existing energy plant, so it means that it is easier and most important, more cheap to build. For example, in Rovaniemi, I will tell about our pilot plant soon. It handles 60,000 people's cities sewage sludge, and the footprint of the building is 300 square meters, so you can get some idea what we are talking about. I think you all know as well as I do that why we need to find out some new solutions for wastewater treatment. Activated sludge process was developed almost 100 years ago. At that time we didn't have any idea about microplastics. Now we are soon dealing with nanoplastics, and God bless us what we are going to find when we are able to do that. We have noticed already that the more we study about those organic compounds, the more unpleasant truth we are finding. For example, there was a couple of years ago a study about microplastics in oceans, and the idea was that we all know those 5 big rivers in Asia, and how we are saying that those are causing lots of problems with plastic waste. At the same time, we took a reference sample from one pure Finnish lake, and we find out that actually there were as much microplastics in Finland than there are in those Asian rivers. And now we are trying to figure out why is that, but what we know for sure is that, for example, the amount of the plastic has doubled during the last 14 years, and it seems that the same kind of development continues also in the future, so we have to be careful what we are doing with our wastewaters in the future. Here we are talking about phosphorus, but based on what kind of comments we are getting from our potential customers all over Europe and other continents as well, is that main reason why they are willing to find a solution, thermal solution for the municipality wastewater sludge treatment is to prevent circulation of unwanted compounds, put a stop to the chemical cycle. Another reason is that they want to stop the circulation of harmful nutrients, meaning mostly ending up to the different kind of waterways. And on the third place is this how to extract and utilize nutrients safely. Of course, we want to have this utilizing nutrients coming up in this table, but today it is not the question from the customer point of view. In bigger cities there are questions about traffic jams. You know that sludge contains mostly water, so it is not wise to transport water from place A to place B if that is not necessary. If we are able to handle sludge locally on the place, we can take 1 truck of ash instead of 10 truck of sludge. Our technology is based on patented circulating mass dryer and reactor. It can be used after the wastewater treatment plant, or if there is a biogas plant after the treatment plant, that is okay for us. Then we maybe have to try the sludge a little bit more, but from 20-23% of dry solid content, no additional fuel is needed. Once we have heated up our process, we can just put the sludge in and it has enough energy to continue the process. Here we can see the quite simplified picture of our process. On the left-hand side we have wastewater treatment plant or the biogas plant. We take the wet sludge to the up of the silo, then we use quite traditional centrifuges to dry the sludge up to 20-25% dry solid. Once we have heated up our process with wood or gas or oil up to 855 degrees, we have hot sand coming from the reactor to the dryer. We try to keep the temperature in 110 degrees Celsius so that we are losing only water, not any organic compounds of the sludge. After that, when the sludge meets the hot sand, it continues its way to the reactor, and the heat is enough to incinerate the sludge and give us some extra energy to continue. It is important to understand that main purpose of this technology is to sludge disposal, not to produce energy, but still we are getting approx 1 megawatt hour of thermal energy from 1 metric ton of sludge when the dry solid content is 25. Then we are also getting clean flue gases that goes up in the air and 2 fractions of ash. We have been discussing here how to use and how to extract phosphorus out of the ash. Actually, as a company, we are not there yet, and we are here in this conference to meet partners maybe to do that in future, and we are very willing to communicate with you and collaborate with you in different kind of projects in future. What we have found out this far is that actually there is lots of need for forest fertilizers in Finland and Scandinavia, and because we are using that much iron 3 sulfates in our wastewater treatment plants in Finland and Sweden, the phosphorus is not in very soluble form but for the forest fertilizers it is only a good thing, so that is why we have been not that active to find ways to change that situation. If you can find some figures from my presentation or from our websites, those figures are quite conservative. For example, we are telling here that 5% of the ash will be the byproduct ash. Now it seems that it will be only 1% from our pilot plant, so much better situation than we were thinking. Also, the phosphorus content of our ash should be somewhere in 8%. Now we can say out that it is at least 5%, but we are dealing with the wastewater treatment plant and of course with our own process that we can reduce the amount of iron phosphates and amount of silica. Okay, sorry. I ran out through this presentation, so I am happy to answer to your questions and continue discussions with you. I was expecting to show you some slides about our plant in Rovaniemi, but in this version they were not available. Today we are handling 10,000 tons of sludge in city of Rovaniemi. Our process is working quite well. We have been dealing with many issues like in pilot plants used to be, but nowadays we are running the plant, not unmanned yet. We have a couple of guys observing and making the, if needed, manual operation, but it seems that now it works and we are ready to look after the new challenges as well. Thank you.
Thank you. Now we have a short video which I'm hoping will automatically play. Looking to the technical guys. And then we'll have questions.
Técnicas Reunidas, in collaboration with the Swiss foundation ZAR, is developing a new technology known as Phos4Life to recover technical-grade phosphoric acid from sewage sludge ash. Phos4Life is being developed at Técnicas Reunidas José Llado Technology Center in Madrid, Spain. Phosphorus is an essential nutrient for life and plays a key role in fertilizing crops and achieving and safekeeping food security. A growing world population is driving the need for larger quantities of fertilizers, and the demand for phosphorus is steeply rising. Mineral phosphates, the source of phosphorus, are relatively abundant, but they are a finite, non-renewable resource. Phosphate resources are scarce in Europe, who depends entirely on imports. This has led to the classification of these minerals as critical raw materials for the European economy. The main course of action to remedy this situation is to implement a sustainable use of phosphorus, minimizing losses during its life cycle. With phosphorus recovery and recycling, the consumption of mineral phosphates is reduced, and the detrimental effect of phosphorus on aquatic ecosystems are eliminated. Phosphorus recycling is an important step forward for the environment and the circular economy. The Phos4Life technology consists of 4 main steps. In a first step, sewage sludge ash is leached, transferring phosphorus into the aqueous solution. This is followed by 2 solvent extraction steps to obtain pure phosphoric acid and a commercial iron byproduct. Heavy metals are recovered from the sewage sludge ash, In a final evaporation step, technical grade phosphoric acid at 75% concentration is obtained. Phospholife technology contributes to sustainable development and the circular economy, reducing pressure on our environment. Phosphorus recovery eliminates the detrimental effect of sewage waters on the environment and preserves mineral phosphate resources.
We have a few minutes for questions, so I'd like to welcome all our presenters back up onto stage. Okay, they're all just about here. So does anyone in the audience have a question? Oh, there's two people who've already. I'll ask this gentleman here in the blue shirt. If you can pick one question and then we can go to someone else.
If I understand your question correctly, you're asking about the competition between vivinite and other precipitates? Phosphates? Yeah, what we see is that first iron will react with your sulfides, and that iron is partly lost, so that's always an offset that you have. And after all the sulfides are bound, you selectively bind the phosphate. And then vivinite has the lowest thermodynamic base, so it will compete with the phosphate for struvite. So if there would be phosphate in struvite, the iron will take away the phosphate from the struvite. And that's the nice thing about the vivinite, so you will always end up with just one precipitate if there's enough iron present in your sewage sludge.
Okay, I'm going to ask this gentleman in front of me here.
On the second question, we roughly a little bit more than double the ammonia N content, right? So the mineral water soluble, we a bit more than double that, and that is based also on the fact that we actually steer it on the pH. So pH is an important factor for us. So we bring the pH between 5 and 6, and that is one of, you can put a target into the machine, and then we make sure that the pH goes in that direction. And that's also a bit of the answer on the other question, is that reducing pH and the sanitation effect of the reactive plasma gas make sure that the environment for pathogens and bacteria is actually bad. So methane producing bacteria actually are not producing methane anymore, as an example.
Okay, I'm going to allow one more question. Anna, I can see over there.
Yeah, so I don't know if people understood the question. So some of the phosphate in your digested sludge cannot be trapped by the iron because it's in the organic phase, and then you cannot get to that phosphate. That's what we see in normally digested sludge. That's 10 to 15% of the total P. And the question was if you would add thermohydrolysis and you would break down this organic matter, then indeed I think some of the phosphate would be released, and then you could theoretically increase the recovery percentage, I think. No, we have not looked at that yet. No.
Right. I'm really sorry, but we don't have any other time for questions, as we need to make sure we go into the next session on time. Please do find the presenters in the break time and ask them your questions. But I'd like to give another round of applause to our presenters, please.